welcome. Now we will discuss multi-way ANOVA. I hope that you have understood one-way ANOVA, two-way ANOVA, so now we will be discussing multi-way. Multi-way means 3 or greater than equal to 3 factors each with greater than equal to 2 labels. For example, suppose you consider 3 factors A, B and C, A with A number of labels, B with B number of labels, C with C number of labels. Then this is 3 factor model, and it may be something like in our radar scope example, this one is our ground clutter, A is ground clutter, B is type of filter, C can be anything some other factor. For example, if you have skill operator plenty in number, so you can also control the operator. So that means the operators can be controllable in that case. So then the 3 different level at 3 different factors, each with different labels. Ground clutter 3 labels, this is 2 label, this may be, suppose you have 10 different factors operators who can be considered. You have available this. So this is 3 level. Now what happened, you may find that there are more number of factors, D, E, many more. So then D will be 1, 2 at each with D labels, E will be 1, 2 each with E labels. Similarly, you can go up to K number of factors, K number of factors. K can be any value. If K equal to 1, this is 1 factor C experiment, K equal to 2, 2 factor experiment, K equal to 3, 3 factors experiment, K equal to 4, 4 factor, K equal to K factor experiment. Now when we are talking about multi-way ANOVA, you please understand that we are basically considering an experiment with multiple factors, which means 3 or more number of factors. Okay. So there is a complete randomized design CRD, let CRD with 3 factors. So what will be your data set? What will be your experimental settings? So A, B, C. Now A level 1, B level 1, C can be level 1, 2 like C levels. A level 1, B level 2, C can be 1, 2 C levels. Similarly, what happened? Again A A level 1 and then B level B, C will be 1 to C. In this manner, A level, then finally B level, and C will be 1 to C levels. So how many experimental settings will be there? A, B, C. If A equal to 3, B equal to 2, C equal to 10, then you have 10 into 20, 60 treatment levels, treatment combinations, not level, treatment combinations. Suppose you have done 60 treatment experiment with 60 treatment combination, and again each level, each combination you have 1, 2 like n number of observations. So, essentially then you have ith index for factor A, jth index for factor B, kth index for factor C, and lth index for number of replication. So, essentially your number of a general observations will be represented like y I j k l. This is I for factor A, j for factor B, k for factor C, l for replications. So, this is the general observation. So, when you conduct experiment, complete randomized experiment, you will be getting random response values y I j k l, where I varies from 1 to A, j varies from 1 to B, I varies from 1 to A, j varies from 1 to B, k varies from 1 to C, l varies from 1 to n. Okay. So, if there is one more factor D, then what will happen? Your general observation y I j k l m. So, I for A, B for j for B, k for C, l for D, and m for replications. Okay. So, fine, when you increase the number of factors, so what is happening? Your sources of variation is increasing, source or sources of variation. So, it is analysis of variance, and sources of variation are very important. So, what will be for 3 factor case? What will be the sources? A, B, then their interaction, then C interaction AC, BC, another interaction plus error. What is happening then? You are having A factor which is known as main effect, B interaction is another main effect ME, AB is interaction effect IE, C is again another main effect, AB, AC, these are all, and ABC, these are all interaction effects, and this is the random effect error. So, depending on the number of factors k, depending on the k, you will be having different kind of effects. So, if you experiment with k factors, then your main effect will be k numbers, interaction effect will be of different kind. First is 2 interaction, 2-way interaction. So, this will be kc2 numbers, 3-way interaction, this will be kc3 number, like this k-way interaction, that will be kck means 1. So, if I consider k equal to 3, in that case main interaction is A, B, C, that is 3 numbers, 2-way interaction is A, B, A, C, B, C, again 3 numbers, and 3-way or k interaction is A, B, C, that is 1 number, C3 3 is 1. So, how many sources you are getting? 3 main effect source, 3 2-way interaction source, another one is that ABC, that 3-way interactions. Okay. So, ultimately 1, 2, 3, 4, 5, 6, 7, 8, another one error is there. Okay. So, essentially by sources of variation, in we are talking about the variation of that you will observe in case of 3 factor experiment y I j k l data. If you see that there is a total variation in the data, some data, but data will vary, value will vary, and there will be variation, and as a result this total variation can be decomposed into so many variation levels, so many parts, for A, for B, for C, for AB, AC, BC, ABC, and error. Now, if you go for 4, then what will happen? Your interaction effect will be 4C2 means 4 into 3 by 2, that will be 6, that is 2 OA interaction will be 6, 3 OA interaction will be 4C3, 4 by what will be the 4C3 means 4, then 4C4 means 1. So, in that way you have to find out the interaction, accordingly you find out the sources. You may argue that okay, there are 2 factors, so 3 factors, so 3 source and one random source, fine, but in a multi-way analysis of variance or even in analysis of variance case, that a main effect are the source, but their interaction you can also consider that the source, because if there is no interaction, if you the change will be there. So, accordingly we will partition the things. So, a general observation y I j k l, this will be partitioned into what it will be? There will be grand mean or grand average, there will be A effect, there will be B effect, there will be AB effect, there will be C effect, AC effect, BC effect, ABC effect, and error will be there. That is what we will do. And so, accordingly, what you will write y I j k l, this general observation, you can write this equal to mu plus tau I. Mu I is grand mean. This is the overall population model. So, grand mean, tau I for factor A, beta j for factor B, plus gamma k for factor C, plus tau beta I j plus tau gamma I k plus beta gamma j k plus tau beta gamma I j k plus epsilon I j k l. This is your 3 factor ANOVA model. 3 factor ANOVA model. So, I from 1 to A, J varies from 1 to B, K varies from 1 to C, L varies from 1 to N. So, we are considering balanced ANOVA because sample size equal, and it is better to consider balance, and this is your error term. Now, if you want the estimate thing, so what will happen? What are the estimated value? Mu estimate will be, where is this? So, this will go for y dot dot 4, that bar. This one will be y I dot 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 bar minus this. Similarly, for this, that means what will happen? I dot j dot dot bar minus y dot 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 this. K will come, and ultimately interaction effects you have to find out. So, that is similar manner the way we have done for 2 factor ANOVA or 2 OA ANOVA case. Now, let us see the calculation part. So, you see what you want? You want to compute SST. I am not going into the further partitioning effect because all that the concept remains same, you know all those things. So, let us see that what is SST. That means you are talking about squaring each of the observations and then taking sum, and you are subtracting the subtraction factor. This is nothing but again the total square, grand total square by the number of observations. Then you find out SSA, SSB, SSC, then you find out SSAB, SSAC, SSBC. When you are finding out SSAB, you require SS subtotal for AB. When you find out SSAC, you require SS subtotal for AC, and similarly for BC, SS subtotal for BC, and this is the formula. And once you have all those things as well as your SSABC, then SSABC subtotal and this, then you can find out find out SSE, that SST minus SS subtotals A, B, C. Okay. So, this is just a the equations are not tough, it is just it looks a big equation, but concept remains same like in 2 factor ANOVA case or 2A ANOVA case. Only you please be careful about the formula on what is to be divided. For example, when you calculate SSA, then BCN will be divided from the sum of the individual squares. When for B, ACN will be divided. Similarly, when you calculate interaction, the subtotal is very important. Okay, that subtotal, which subtotal is relevant for which kind of interaction, that you have required to be understood, and through practice it is possible. Okay. So, then you will definitely prepare this kind of ANOVA table, and again you see that all A, B, C, A, B, A, C, B, C, A, B, C, error and total. I have discussed this source of variations. Then you find out sum square SSA, SSB, SSC, SSAB, SSAC, SSBC, SSABC, like this. Then degrees of freedom A minus 1, B minus 1, C minus 1. A minus 1 into B minus 1, A minus 1 into C minus 1, B minus C minus 1, like this, A minus 1, then A B C into N minus 1 and A B C N minus 1. Divide SS by their respective degrees of freedom, you get mean squares. And here we are introducing one more concept called expected mean squares. From theory, you know that it will be like this, and although I say you know, but we have never discussed this. Please keep in mind that it is expected that so every source of variation has some effect. In that case, this is the quantity BCN tau I square by A minus 1 or ACN beta j square by, this is the quantity which is added to sigma square, because sigma square is the quantity which is the random variation and which is related to primarily related to error. You see that SSE and MSE calculate, and then the expected mean square, that means expected value of MSE will be sigma square. So, this interesting thing that also in the earlier cases we can introduce the same thing, but here the interesting thing is that when you are calculating F0, you are basically comparing MSA with MSE. Now, that means the expected value of MSE is sigma square. If there is no significant difference of the different treatment levels, for suppose for factor A or B or C, then this will coincide or will be almost equal to MSE. That means this quantity BCN sig tau I square by A minus n or ACN, this added quantity, this will become 0. So, that means the variability is all equal to sigma square, which is equal to MSE. If there is difference in that expected mean square, then each of the sources are contributing towards the difference. That is what is interesting to you. Anyhow, suppose you have only 2 factor case A, B and A, B and error. In that time, only this B, C and A, that terminology, suppose B, C and A, here B, C is coming because it is a 3 factor case. So, B, C, B n will be there, C will not be there, but in the same manner this can be computed. Now, there will be tabulated value for F. For A, tabulated value will be F. What will be the tabulated value for A? F alpha A minus 1, and in this case what is the error degrees of freedom? A, B, C into n minus 1, usually alpha equal to 0.05. Now, if your computed value for A, this is greater than this tabulated value A minus 1 A, B, C into n minus 1 alpha, then this has effect. Similarly B, similarly C, similarly like this. Okay. So see one example. The process engineer can control 3 variables during filling process. The percent carbonation, which is denoted by A, the operating pressure in the filler denoted by E, B, and the bottle produced per minute or the line speed denoted by C. Actually, this is basically that Coke making, Coke in the Coca-Cola or something like this, the filling the bottle. Now, the engineer can control carbonation at 3 levels, 10, 12 and 14%. She chooses 2 levels for pressure, that 25 and 30 psi, and 2 levels for line speed, 200 and 250 bpm bottles per minute. She decides to run 2 replicates of a factorial design in these 3 factors with all 24 runs to be taken in random order. The response variable is the average deviation from the target fill height observed in a production run of bottles at each set of conditions. The data that resulted from this experiment are shown in the next slide. Positive deviations are fill heights above the target, whereas negative deviations are fill heights below the target. What is happening here? The situation is like this. Suppose you have a Coke bottle. So, you want to fill with Coke. There are one is factor A, that is carbonation. It is having 3 levels, 10, 12 and 14%. There is factor B, which is basically pressure at which the bottle will be that Coke will be filled, that is 2 levels, 25 and 30, and another one is that what speed you are basically filling the bottle, that is C is 200 bottle per minute and 250 bottle per minute. So, this is the feed ratio, that is line speed. Okay. Now, so that means what happened, your A 1, 2, 3 levels, B 1, 2 levels and C 1, 2 levels. In total, how many independent treatment combinations are there? 3 into 2 into 2, 12, which is A, B, C. But the engineer decided to conduct 2 number of replications. So, in each setting there will be 2 replications. So, K equal to I, J, K, L, L equal to 2. So, that means your total number of runs will be 12 into 2 equal to 24. What I mean to say, Y, I, J, K, L, this value, the total value will be, how many such observation you will get? You will get 24 such experimental data. Okay. Now, see this. Here you see that this one, this completely, this is the tabular representation. Please remember, again I repeat, we have taken from Montgomery book. Percent carbonation 10, 12, 14, your operating pressure 25, 30 and then line speed 200 and 250. So, how many observations are there? 3 into 2, 6 observations, and again replication 2 each cases. So, 12 observations here, 12 observations here, 24 observations. You see the right hand side, SST calculation. That means you find out the square of each of the 24 y values, y, I, j, k, l square. So, this value once you, and then you are subtracting by the grand total value, which is, when I summing up all those things, this is 75. You may be thinking that what is this minus and plus? Basically, this is nothing but, suppose you want to fill up to this level or up to this level, let it be. So, this is, suppose this is the H height, this should be filled. Now, in bottle 1 you measure and you find out that this is the gap. bottle 2 you measured, maybe this is the gap. So, if this is the target, let it be this is the target which is H, then this is positive more than target, this is negative less than target, it is there. So, in that manner 24 experiments are done, and in each setting 2 bottles, 2 experiments are 2 replications are there. Like in the first case is -3 -1, second case may be 0 1, like this is the field to the target. So, response variable y, this is basically deviation from target filling. Target is H, this much will be bottle will be filled, and if it is less that or more, then that will be represented by y. So, this formula, now SS carbonation means basically SSA. This is the equation you have seen earlier, and then what you are doing 1 by BCN y I is changing. What is I here? I is basically this one, first row, this related to 10, 12, 14, and you see what you are writing here, -4 square plus 20 square plus 59 square. What is this? This is basically the row total. So, in the first row related to carbonation, this is 10, here everywhere 2 replications are there, and ultimately the total is -4. So, -4 square, second total is 20, and like this, and you divided by BCN, B is 2, C is 2, and N is 2. So, 1 by 8 you are getting like this one. Similarly, find out SS pressure, SS speed, and then SSAB, which is basically the subtotal is this is the subtotal 1 by Cn Ij square, and then Ij this one, this is the subtotal, and these are the SSA, SSB will be subtracted. Now, subtotal Yij, I stands for A, for A I, and for J it is basically, for J is operating pressure for B, then dot mean the total. So, that means 25 PSI, 10 A 10, so how many observations are there? So, how many observations are there? 1, 2, 3, 4 observations are there. So, what is the total of this observation? Here this total is -4, this total is -1, -4 -1, that is -5. So, in this manner you compute and get this one, and similarly for other values also, SSAC, SSBC, SSABC, and like this, and finally and SS sub total ABC also you get it, and then you calculate SSE, SST minus SS subtotal, this is the value. And once you have all those SS values, you create ANOVA table, degrees of freedom known to you, mean square you can compute, F0 you can compute, and P, here we have given P value, but it is approach it is because P value computation is tedious. So, what you do basically you choose alpha equal to 0.05 or some other value, but usually alpha is 0.05, and then find out F value for this alpha given degrees of freedom nu 1 and nu 2, and nu 1 will be this, if it is A 3 level, so it will be A minus 1, so that means 2, and nu 2 always for error degrees of freedom, error DOF. Here in this case error DAF is 12, so it will be always 12. Now, if this value is less than the computed value, H0 is rejected, means there is factor A effect, similarly factor B effect, factor C effect, like this. Okay. Now, see all three. Here what have happened? All if you see this one, that first one, second one, third one, they are basically significant because P value is much less than 0.05. So, these first three significant. If you see the AB interaction here, the value is 0.0558, this is just above 0.05. So, you may say this is not significant, but if you consider that this is 0.06 is almost 0.05, and you can consider also AB effect, but other probability values you see P values are very high. So, these are not significant. So, all three summary, all three factors significantly affect the field volume, and there should exist some interaction between the factors. Okay. So, this is what is your three-way ANOVA. Okay. So, you can think of that there can be more than 3. Okay. So, I hope you have understood also three-way ANOVA and then calculations, and if not, please write in the forum, and we will see in the forum, and our TAs will be seeing the forum, and they will be giving you the reply. But up to this, I want to tell you one very important thing. That means that first is selection of factors, and when you do experiment, you must know selection of factors. How many factors? Here number of factors is very important. Here number of label is also very important. So, once this is done, you are in a position, you know that what will be the treatment combination. This will help you in finding out the treatment combination. Suppose if I say 3 factors, then your treatment combination is ABC. Once you know the treatment combination, then you will select that what will be the replications, number of replications. So, replications is n. This will help you to find out that what is the total number of experiment that you have to conducted. And then you just see that you cannot conduct this n number of experiment arbitrarily. There will be complete randomization design. Then what happen after that, that design you have to do, and then conduct experiment. Once you conduct experiment, you get a data, you get data table. So, you will get yijkl, or if it is 3 factor, if it is 2 factor yijk, if it is 1 factor yij. So, 3 factor case, 2 factor case, and this is 1 factor case. Once you this is prerequisites for, because these are the things you that is what you have done actually, and this data set is available. Now, you analyze the data set. If it is 1 factor, you go for 1-way ANOVA. If it is 2 factor, you go for 2-way ANOVA. If it is 3 factor, go for 3-way ANOVA. If it is 4 factor, 4-way ANOVA, and if it is 10 factor, 10-way ANOVA. All these are known as multi-way ANOVA. Okay. Another, and everywhere, because we are interested to know whether factor effects are there or not, and interactions are there or not. Your hypothesis will be concerned with the factor effects, it will be main effects, hypothesis, all hypotheses related to these interaction effects. And this actually main effect and interaction all are compared with the error, which is MSE. If the variability explained by the main effect is equal, is similar to MSE, mean variability similar to MSE, then there is no effect. If there is factor effect, it will be much more than the MSE. And then F test, tabulated value, computed value, comparison, and you will find out which is effective. This is what is in nutshell ANOVA. And this ANOVA model has similarity with regression also. So, we will discuss regression in subsequent classes, lectures. Thank you very much for your patient hearing. Thanks.